Hello everybody, in this lecture we will be solving 1988 IMO problem number 6. This is a number theory problem. We're given a and b positive integers such that ab plus 1 divides a square plus b square. So therefore, this given fraction, let's call it as q is a positive integer. And whenever that's the case, so this fraction happens to be a positive integer, it must further be also the square of an integer actually. So q is a perfect square, so we need to show that. So we need to show this. Let me recast this in the following way. So I will say that AB, the pair AB solves the following expression: x squared plus y squared, after I do cross multiplication here, equals q times xy plus 1. So this expression is equivalent to this one. So the given expression here is equivalent of saying this. So we know that AB, the pair AB, so if I replace x with A and y with B in this equation, that's a solution. So that satisfies this condition, right? So let's call it condition 1. And what I'm interested in, before though, let me remind you that a and b are both positive integers. So what I claim is a and b are obviously not the only solutions. There's an infinitely many parameterization solutions of this equation, and let's consider on a pair of non-negative integers. So consider this pair KL, which is what? Z plus including 0 times Z plus including 0. So KL is a non-negative pair which satisfies this equation, satisfies 1, but moreover, it is also minimal in the sense that K plus L is minimum. So I'm invoking here the extremal principle again. So because K and L are perfectly symmetric with respect to equation 1 here, without loss of generality, we can assume that K is less than or equal to L. And in fact, I can further assume that so this implies that L must be also greater than 0. Why is that? Because if L is 0, it means K itself is 0, because we are picking non-negative integers. When both of them are 0, 0, 0 is not a solution of equation 1. As a result, L must be greater than 0. K can be 0 or greater than, but L is definitely greater than 0. So what I will do is I will recast 1. So 1 is equivalent to the following form, to the following expression. After I organize it and I rewrite it carefully, qx minus y equals x squared minus q. And let's call this one as equation 2. And consider the following integer. So consider the following integer j, which is equal to qk minus l. Because k and l, the pair KL solves equation 1, we already know that, so x equals k and y equals l satisfy equation 1, satisfy 1, and as a result this implies that replace y with l, and now replace x with a k and minus l again. So that thing is equal to k squared minus q from equation 2. But then, I just realized that this is just from my definition here, this is just a j, so therefore I come up with L times j is equal to k square minus q, but just notice that k square minus q is strictly less than k square because we know that q is a positive integer, and k square because of this inequality is less than or equal to L squared. So what this implies is that because L is a positive integer, if you cancel L from both sides of these inequalities, we'll get that J is strictly less than, strictly less than L. So that's crucial. Now, please have a look at the following expression. So let me change color. So consider this line here. In this line, let us replace L. So from this expression, we realize that L is simply equal to qk minus j. So therefore, in this expression, if I replace L with this one, so this implies that q times k minus j times, well, look at this one. This one is simply equal to j, right? Times j is equal to k square minus q. But just rearranging, we will get back to the original equation. Actually, what this means is that this implies that kj also solves the equation the equation 2, right? So that's kind of this is our original problem. So our original problem is equal to expression 2, but then if I can rewrite it like this, you just realize that compare these two expressions, it's immediate that if you want, you can replace these two on the left hand side. So but that's the same thing. So y is replaced by j and x is replaced by k on the left hand side, and on the right hand side again x is replaced by k. So therefore jk satisfies this, but because kj solves equation 2, but because j is less than, strictly less than L, this implies that k plus j is strictly less than k plus L. But remember that k plus L is minimal, minimal by construction, by definition, for what? For non-negative solutions, for non-negative solutions. So therefore, this implies further that j itself must be a negative number. Now recall that j is equal to qk minus L. So therefore, this further implies that qk minus L is less than 0. Or rewriting it again, we get that qk is strictly less than L. And finally, knowing that j is less than 0, because j is an integer as well, j must be less than or equal to minus 1. So since j is less than or equal to minus 1, but then this is equivalent of saying that minus j is greater than or equal to 1. So combining this with the final result here, so I will just multiply these two inequalities. Remember that minus j is positive, so therefore multiplying these two inequalities will not change the sign of the inequalities. So let's call this 3 and 4. So multiplying 3 and 4 will imply that on the left hand side I will get qk, and on the right hand side I will get minus L times j. But minus L times j, remember, is equal to from equation 2, L times this one was equal to j, so it's just equal to k square minus q. K square minus q. Now Actually, no, it is with a minus sign. Sorry for that. So there is a minus sign in front. So therefore, this is actually q minus k square. Okay, so this is even better for me. Now I can just move q to the left hand side. So this q here, I will move to the left hand side. So this implies that, and I'm factoring out that q, I will get k minus 1 is strictly less than minus k squared. And as a result, because q itself is positive, right? Remember, q is an integer greater than or equal to 1. So so therefore, what this implies is that because the right hand side is negative, it must be that this guy is less than 0, right? The right hand side is definitely less than 0 because so therefore k minus 1 is strictly less than 0. But remember, k is an integer, so the only integer that will satisfy this, so, or let me rewrite it. So k is less than 1. The only non-negative integer less than 1 is that k must be equal to 0. So for the minimal k plus l pair, so the minimal pair that satisfy equation 1 and 2, for which k plus l has a minimal sum, must have k equal to 0. But because q is fixed, so when you plug in k is equal to 0, and for y, so let's say that now plug into you can plug into equation 1, for instance, into 1, x equals k equals 0 and y equals l, which is greater than 0. So what we get is that so from here, plugging in the numbers, recall equation 1, so which is x squared, let me just write this, so which was x squared plus y squared equals, so x is 0, so 0 squared plus y squared is just l squared is equal to q times x is 0, 0 times l plus 1, but the right hand side is simply equal to q, so suggesting q is equal to l square. So from here, q is equal to l square, and it is necessarily a perfect square as desired. Now we are done with this problem, but we can get much more insight into this problem actually by investigating the equation, and I would like to spend some time on this. I highly recommend you also check that with me. So consider this expression here, equation 1. So what does it represent in the coordinate system? So what type of graph will I get? So the answer depends on the value of q. So here is, so let's rewrite that. So we have that x squared plus y squared is equal to q times xy plus 1. So I claim this is so this was equation 1, if you remember. So this is an ellipse, the shape of an ellipse if q is strictly less than 1, and it is two parallel lines. Actually, if q is less than 2, my apologies. Okay, so let me rewrite this carefully. So if q is less than 2, it turns out that this equation is an ellipse. If q is equal to 2, it is two parallel lines, and if q is greater than 2, we'll get a hyperbola. Okay, so why would that be? Here you go. Let me for instance investigate this case here. So this one is almost obvious here. So consider for which value of q will we get a perfect square on the left hand side. So if I plug in q is equal to 2, sure enough we'll get x squared plus y squared minus, so I can move that to the left hand side, 2xy is equal to 2. So this would imply that x minus y squared, oops, that's a square, is equal to 2, suggesting that x minus y is equal to plus minus root 2. So basically you have two lines which are parallel, they go through these points root 2 here, negative root 2, and again root 2 and negative root 2. Oops, sorry for that. But that's obvious. So you would get two parallel lines. So these two lines are parallel. So when q is less than 2, for instance, if q is equal to 1, so we would get that x squared plus y squared is equal to xy plus 1. Q is simply equal to 1, implying that x squared minus xy plus y squared is equal to 1. You can simply test some values and, for instance, and immediately guess that it would come out as an ellipse, or you can actually factorize this expression carefully and you can come up with a common format of the ellipse. In fact, I was very lazy on this one and I did use Wolfram alpha, so shame on me, I guess, and look what I've found. So our expression when q here is obviously equal to 1, Wolfram alpha plots it very, very nicely. So our ellipse will go through 1 minus 1 here and 1 minus 1, and it will also go through the point 1, 1 here and minus 1 here. So therefore, going back to this thing, so the way to draw it, so this was the case when q is equal to 2 here. If q happens to be equal to 1, we get this very nice ellipse which goes through 1, minus 1, minus 1, 1, and in fact it also goes through the point 1, 1, and minus 1, minus 1. So we have 6 points of the ellipse. You know, to uniquely construct an ellipse, in fact 5 points is more than enough. Well, enough actually. So our ellipse would look like that. This is 1, 1, this is 1, 1, this is minus 1, minus 1, and minus 1, minus 1. Okay, finally you just realize that if q is strictly greater than 2, then that's the case which is quite interesting, and this is the case where we have our problem here. In our case, we would have x squared okay, so x squared plus y squared is equal to q times xy plus 1, and here where q is strictly greater than 2. So let's test it on Wolfram alpha. So let me just replace this 1, the product by 1, with say the number let's say 3, and when you say enter, it will start the computation, and boom, we have the shape here. It's not surprising to find the intercepts, which is I think root 3 here, because if you substitute x equals 0 here, this one will be removed, so you have a 3 on the right hand side, and on the left hand side you have a y square, so therefore you'll have a root 3 plus and minus on the both sides. So therefore our solution will look like this. So for instance, for q is equal to 3, our solution looks like pretty much like this. So you have root 3 here, negative root 3, again negative root 3, and root 3 here. So therefore you have this, let me use another color, this nice hyperbola shape, like that and like that. So the hyperbola obviously will have two arms. Now what we are interested in this configuration is under what conditions the solutions will be such that you get lattice point solutions on these graphs, right? So that's kind of the idea. So we are not interested in the whole plane, we are only interested in the lattice point plane. So how do I know, oops, sorry for that, how do I know if a given hyperbola will ever go through any lattice points? So that's the critical observation. And it turns out if you keep testing on Wolfram Alpha, for instance, if you scroll down, Wolfram Alpha will give you the real solutions of this, and that's it. You can see how y depends on x, but these are all real solutions because you have all these radical expressions. But interestingly, if you change the 3q, instead of 3, you replace it with a 4. And why is 4 so important? Well, because it's a square, right? So that was the problem in so then our thing goes through the point 2 0 here, 0 2 minus 2 0 and so on. So but what's so interesting is as you scroll down, not only Wolfram Alpha will give us the real solutions of this, but it will also give you the integer solutions to this hyperbolic equation, right? This hyperbola equation. So this is quite a surprising result that gets us thinking. Thinking about the deeper meaning of this. So for instance, for q is equal to 4, we just observe that not only our hyperbola goes through these minus 2, 2, minus 2, these integer points, which is awesome, right? So that's what the question was asking about. But moreover, the claim is that there exists a parametrization which provides an infinite number of solutions on this graph, and the way to do it is to build it recursively. So let me create the recursion and let's discuss this recursive equation together. So the question is basically telling you that if q is not a perfect square, then our equation, let's write that down. So oops, sorry for that. So we have two parts of the thing. So in the first part, let's call it part 1. So we say that if q is not a perfect square, then the equation x squared plus y squared equals q times xy plus 1 has no solutions in lattice points, right? Has no solutions in integers xy, right? Or pairs of integers. Okay, good. And the second, and by the way, this was actually the question that we just solved, right? But we can do even better. We can actually characterize all the solutions. So here is the characterization, which is an awesome result. If and this is due to not me, Marcin Kurzma, which is, I believe, a Polish mathematician, and he used to propose quite a few problems during the 1980s and 90s for the IMO. So I'm taking this from his book, and here is his claim. So if Q is actually a perfect square, then so obviously like what, like this one, the one that we did together, L is a positive integer here, then we can characterize all the solutions in the following manner. So x0 is equal to 0, so your initial conditions, two initial conditions, x1 is equal to L, and finally the recursive formula xn minus 1 plus x sub n plus 1 is equal to q times x sub n for n integers. Now this is beautiful. So you have an increasing sequence of integers, and I claim that the following pairs, the pairs x, y, which are equal to x sub n plus 1, in this fashion, for n in integer, satisfy the main equation, satisfy x, satisfy x squared plus y squared is equal to q times xy plus 1. But moreover, and moreover, they completely characterize it, right? So moreover, this pair, so x sub n plus 1 is a complete set of solutions, complete set of lattice point solutions, lattice point or integer coordinate solutions. So this is a very, very nice result. So the Olympiad problem was just asking for the first part, but the first part by itself is not very informative. So if we can prove the second part, this is the strong thing, right? So this is the really good stuff. So we already have an idea on how to proceed. So I will just focus my attention on for the case where Q is greater than 2. So I have a hyperbola, right? So let's fix Q as an integer, as an integer greater than or equal to 2, actually. Yeah. Q is an integer, is a positive integer greater than or equal to 2. Then we will have the shape of a hyperbola, right? So you can think of two parallel lines as a degenerate hyperbola, if you will. So then we will have the following shape. So we will have our hyperbola like this. It will have two branches, and we already learned how to calculate these intercepts, right? So this one, for instance, would be at the point square root of Q, right? It's not too hard to see it, right? So for instance, this is the x-axis. So if you plug in x is equal to 0 on our equation, y squared, you will get the y-intercept. So let me quickly do it. 0 times y plus 1. So the right-hand side is simply equal to q and y squared. So y comes out as plus minus square root q. The minus square root q obviously is this one. So we can just focus on our attention on this branch here, the upper branch. It can be represented by a function f, which is well defined. So the hyperbola is kind of a union of two functions, right? So you can think of them as f sub 1 and or instead, even better, instead of f and f sub 1 and f sub 2, I can just call them f and g. This guy is g. But anyhow, so this is an increasing, monotonically increasing function. It's well defined. And the interesting thing is, whenever I start on a point, any lattice point on this shape, or any point actually, let's just say any point, then you can move from one point to the other using the recursion that we will have. So if you have a point, let's say p sub 0 is equal to x sub 0, f of x sub 0, right? So that's a point on this branch. We are just focusing our attention on this upper branch here. So P is any point on that branch. You can start with a point, and then by using iterations, right, recursions, using your formula f, you can repeatedly apply it, and you can define each of these successive terms x sub n in the following way, right? So you would just repeatedly apply the function f to our point x sub 0 n times here, and then you would find the next point. So therefore point p sub n would simply be equal to x sub n, f of x sub n, but f of x sub n is just x sub n plus 1, obviously, because we are defining it recursively. So therefore, once you have an initial point to begin with, so the function that we have, which is, as I said, which has all these nice features. It is continuous function, strictly increasing, and it maps each of the real axis to the real line, to the real y's here, to the real y-axis here. So as a result, I will have this nice succession of points, right? So what I would do now is, if I'm starting at a nice point, like which point, for instance, at a point q sub 0 is equal to, for instance, at this point here. at the point 0 square root q, I will have a succession of points starting from that point, and I think these are important points. So obviously I need to calculate these, which I'm lazy, I will not do it, but you can successively, using this procedure, you can calculate each of these points. Now what is so interesting is the following fact: due to the nature of this recursion, if our point Q is a perfect square, this recursion tells us that if you start with a lattice point coordinates, then it will, well, if two initial conditions are both lattice points, obviously one of them is, and if Q is a perfect square, the first point will be 0 square root Q, but because square root Q is a perfect square, so 0 square root Q is a lattice point, and the next guy is a lattice point as well, so L, and then so what this recursion guarantees is that this construction here will create a succession of lattice points. But where did this recursive form came from, right? It just is an application of the formula twice. All you do is you plug in the points p sub n and p sub n minus 1 in our formula twice, and you subtract them and you get this recursion. So let me quickly do that. So if I plug in this point into the formula, so I will get that x sub n square plus x sub n plus 1 square is equal to q times x sub n times x sub n plus 1 plus 1. And then if I plug in this point here, x sub n minus 1 and x sub n, what I will get is this one square q times here x sub n minus 1 times x sub n plus 1. And now if I subtract these two expressions, we will see quite a few cancellations here. So this guy will cancel with this guy, the ones will cancel out, and what I will have on the left hand side will be a difference of squares, which I can easily factorize as this: x sub n plus 1 plus x sub n minus 1. And on the right hand side I will have q, and then the x sub times x sub n, and then a difference here, x sub n plus 1 minus x sub n minus 1. Now I can cancel out these two expressions, and boom, I get the recursive form that I wanted. So this is a really nice result. So what it tells you is that if you start as your initial point at a lattice point, this construction will keep so this recursive form, which is valid, will create a succession of lattice points actually. Just to show as an example, notice that if you start with x equals 0, so as your starting point, let's say that you start with, remember we wanted to start with this Q sequence that works. So let's let this Q sequence be the sequence of lattice points. So if you start with Q sub 0 such that x is equal to 0 and y is equal to L, remember that Q is a perfect square, Q is equal to L square, then the construction, the next point will be using the recursion, obviously, right? So this guy here is x sub doesn't matter what you call it, let's call it x sub 0, and let's call this one as x sub 1. So if I now use the recursion to find x sub 2, so I will get x sub 2 plus x sub 0 is equal to q times, q is equal to L square. Yes. I might have done a typo here. No, q is equal to L square, and I'm plugging in, I'm choosing as my initial condition 0 and L. Okay, so yeah, so I think that should work. Okay, so let's try it. So q times, or I should rather say L squared, sorry. So L squared times, so x sub n, so x sub 1. Now let's plug in these values. So we have that, so this implies that x sub 2 is what I want to calculate, plus x sub 0 is just 0, is equal to L squared times, times x1, which is just L. So you would get just L cubed. Yeah. Well, okay, so yeah, so you can either write it like this, or you can well, okay, let's just keep it like that. So therefore our point, so this implies that q1 is simply equal to the following point, with coordinates, x coordinate as being L and the y coordinate as being L cubed. You can think of this as x1 and x2, obviously. But now using these, like we did previously here, using these we can come up with q2, which is just x3 plus x1 is equal to, remember q is just L squared, so sorry for that, L squared times x sub 2, but then this implies, so x sub 3 is what I want to calculate, x sub 3 plus x sub 1 is just L, is equal to L squared, L squared, oh come on, times x sub 2, but x sub 2 is just L cubed. So therefore, this implies that x sub 3 is simply equal to L to the 5th power minus L, or if you will, you can write it as L to the 4 minus 1. Okay, and you can proceed in that fashion, but what it doesn't, so therefore what we found here is that q2 is just the lattice points. Remember, L was an integer, obviously. The lattice points L cubed and L times L to the 4 minus 1. So this is just a beautiful result. Let me just, as an example, for instance, if you try it with q is equal to, say, I don't know, I think I tested it for q is equal to 9, and it works really nicely. Yeah. So for instance, let's try it. So let q be equal to 3 squared, right? So implying that L itself is equal to 3. So in that case, q sub 0 would simply be equal to x equals 0 and y equals 3. So that's my x0 and that's my x1. Then q1 would come out as x equals 3 and y equals, so if you do the algebra, so y should come out as L cubed, which is 27. So this is x1 and this is x2, and finally q2, and you can proceed in a similar fashion, obviously. Q2 comes out as x is equal to 27 and y is equal to, yeah, if you plug in this thing, so you would get so 3 to the 4th power would be 81 minus 1 is 80. 80 times 3 would be 240. So therefore you get your x2 and x3 and so on. So therefore you have your sequence of lattice points starting from 0, 3. Next you will get this nice feature 3, 27, and so on, 27, 240, and you can continue in this fashion. In fact, you can even go in the negative direction as well, but I will not go into that either. And obviously I need to still prove quite a few other things, but I'm already approaching my 48 minutes. We're past half an hour on a single problem. So you can further show that if you have two consecutive integer lattice points in this recursion, that's it. So this will completely describe the whole thing. And if you have so if you have even one non-lattice point, Well, okay, so that part it would not be right. Okay, but anyhow, so that's a very nice result. So that's kind of a very cool result, and I kind of like this problem because, as I said, it gave me the chance to play with Wolfram Alpha quite a lot. So this is a very good website that I highly recommend. So you can work with these numbers. For instance, we did it for 9 here, right? So when you do the computation with 9, you will see that the function will, as we claimed, it will go through the point 0.03 here, and it will further give you some integer solutions. And look at this parameterization. This is just amazing. So like very unexpected. In fact, you can you can even express all this thing in terms of q, but I will not go into that. So I leave it probably to you guys as a homework as well. So we are done for this problem. For our 1988 IMO problem number 6. Hope you enjoyed this this video, and see you in our next lecture.